So thank you for coming. So this is the last class of this mini course. And I decided to do it today with some help of slides, in part because the proofs take a little bit longer, too many approximation terms with this topic, so I decided they're not as clean as the proofs we have been doing so far. So I decided to give more sketches than try to go through all details. So today, essentially, I want to bring the ideas from the previous class, which is to build these uniformly valid confidence regions from linear models to Z-estimators, essentially. So the mindset that I want you guys to have is the same as before. We want to obtain confidence regions for a particular low-dimensional parameter. Could be one parameter. Later on, if I have time, I'm going to discuss how to do actually for many of them. But there will be some restrictions we need to keep in mind. And we are in these high-dimensional settings. So we have this high dimensionality that arises either from having many variables or because we're using some very flexible specification. So we have transformations, have interactions to deal with. And we need to select a model out of that because the theory doesn't really give us the perfect specification. And as I said before, there is a clear distinction between, an important distinction between prediction and building confidence regions. Essentially, confidence regions is a much finer result that a little bit of misspecification because you're trying to build this interval which is shrinking at root n rate. A little bit of misspecification actually hurts you a lot, destroy your coverage, while prediction is much more forgiven. Right? It's really something that one of root n mistakes doesn't really affect you much. And actually, we know that minimax rates are of the order of S log P over N in this setting. So we had to be much more careful here. Last class, in particular, created this distinction between model selection procedures. If it's not clear at all that one model selection procedure that is good for prediction would also be good for confidence regions, in fact, I would argue the contrary. Right? If one works for prediction, the same model selection procedure is likely not to work for confidence regions, and vice versa. Right? Essentially boils down that prediction, you are searching for a convergence roughly on the L2 norm, while confidence regions, especially confidence intervals, you are searching for a norm which is L infinity norm. In the classic case that P is fixed, these norms are equivalent. You can get away with it. But in the case that you allow the dimension to grow, there are fundamental differences between these two norms. And that's why, essentially, the same procedure should not work for both simultaneously. So we're interested in building confidence intervals, allowing for approximately sparse models, and understanding that we are bound to make model selection mistakes in finite sample. I really want to deal with the case that my vector of parameters, the jth component, could be proportional to 1 over j, let's say, cube. So it just decays. So I never have enough separation from 0. So I'm bound to have some model selection mistakes. And if the previous literature up to 2010 was really focused on chasing perfect model selection, which implied bad uniform properties, since 2010, a couple of papers started to work on uniform confidence regions in these high-dimensional settings. The first few results, they were actually for the instrumental variable model, which has a specific structure that made it a little bit easier as a starting point. And then people started working on linear models. That was the paper from myself, Chernouzikov, and Hansen. And then Zhang and Zhang as well. Boomen had a paper into last year. Van der Geer, Boomen, Ritov, posted in 2003 in arXiv, and then later they revised with this Ver for their final version for the ANOS, dealing with linear models with normality and also with generalized linear models. And then I started working on some specialized models to exploit structure. So we have some work for least absolute deviation regressions and Z-estimators, logistic regression. Then Montanari and co-authors actually have a couple of other papers on the topic. Farrell. So it's something that it's essentially exploded now. I think people realize the key issues behind building confidence regions, and now there is a lot to be done to understand specific cases. And I'm going to try to discuss a little bit in the end one of the last work that talks about interesting generalizations. So today I want to focus on Z-estimators, right? And this is a very convenient class of estimators that generalize many things we have been seeing, many things have been discussed. So least squares type of penalty function, it falls into this category. So essentially, this model will be covered. Quantile regression type of models also fall into that. Essentially, we have this condition that the probability that is below a threshold is going to be tau, condition on the treatment and on the controls. And as we saw last time, I'm separating out the treatment from the high-dimensional controls. So I'm going to potentially apply model selection procedures or regularization to beta naught, to try to estimate beta naught. But I really care about the treatment effect. In this case, it's alpha naught. Here it would be alpha tau, could be a quantile-specific effect. Logistic regression, so our outcome is binary, and we have a link function, which is the logit here, that makes this expectation just the probability to be between 0 and 1. Those are 3 examples, but Z-estimators also allow for you to have many other quantities of interest. For instance, if you're interested on the logistic average marginal effect, this is your estimating equation. Essentially, you take the derivative of the logit expectation, but then you average over x. So that becomes the quantity you want to estimate. So in this case, in this problem, theta naught is actually what you're chasing. So everything gets modeled by this setting, right? So generally, I want you to think about, I want to estimate alpha naught, and I have this identification equation. So the expected value of this moment condition, W, you think about the data. So it's like X, Y, and D. When I evaluate this taken expectation with this function at alpha naught and beta naught, this gives me 0. So I can use that equation to identify my problem. And then if you look at the least squares, we have expectation of Y given D and X to be alpha naught D plus X beta naught. So our moment equation there is just Y minus alpha D minus X beta. W alpha beta. Right, so basically, when you take the expectation of this function and you evaluate at alpha 0 and beta 0, you get 0. In the case of quantile, our equations would be our moment equations. So we have probability of Y less equal than alpha tau D plus X beta tau given d given x, that's equal to tau. So our moment equation is actually the indicator function of y less equal than d alpha plus beta x beta minus tau. So when you take expectation of that, this becomes probability minus tau. When I evaluate at those exact points, I get tau gets 0 again. The logistic regression, my function becomes just y minus logit of d alpha plus x beta. Again, if I take expectations, things work. So it's a very convenient framework that allows me to deal with many, many cases of interest in a very unified way. And I'll be concerned with the case that I have only S non-zero components, but the dimensionality of my controls is P is potentially much larger than N. But that's kind of the setting we have been dealing with. And as I said before, we focus on the deriving procedures that are uniformly valid. Essentially, I'm using asymptotic normality statements, but I'm taking the supremum over the data generating process inside my limit. So this should hold for a large class of data generating process. Right? So in particular, it's important to allow for data generating process in which my vector of beta naught is near 0, because that's where model selection mistakes should happen. So that's where we're going to be able to achieve robustness. And just to make sure we are on the same page, when we're talking about doing model selection here, Lasso is one example of how to do model selection. I could do with other ways. But for each one of these problems, if I want to come up with some estimator beta hat of beta naught, I can run a lasso, where the criterion function here, by the way, En is just 1 over n summation over observations, where the criterion function is just the one associated with each problem. Here would be, for the first one, would be least squares. For the quantile regression case, would be the check function we discussed in class 2. For logistic regression, would come from the likelihood function, the log likelihood function. But essentially, we can apply all the techniques we have seen to come up with one procedure to come up with estimates of beta hat. So getting estimates of beta hat should be, at this point, standard. And on top of that, we know how to, if you're using Lasso, we know how to pick lambda. Lambda will be just, in our previous notation, C bigger than the gradient of the Q hat of beta naught. And that we have seen that typically we get this very nice kind of approximation if you use self-normalized model deviation theory. And we also know that we can actually get good rates of convergence for those estimators. So we have this as a startup. That's what we have been doing up to this point. And now, with that equation, a natural way to proceed to estimate alpha naught is to say, OK, that's what I can use to identify my, my value of the treatment effect. So if I have the expectation of M W alpha naught beta naught to be equal to 0, and if I have beta hat estimate of beta naught, one way to proceed is to define an estimator to be argmin of 1 over n summation M Wi alpha. And I plug in beta hat here. I find the alpha that using a plugin that minimizes that expression, where I use a plugin estimator beta hat instead of the true value. And that's kind of the standard approach for this type of problems. The problem that if one hope that this average here would wash away the mistakes you have in beta hat, that intuition works if you are interested in some form of prediction. That intuition should not work in general, or most of the cases, if you are interested in confidence intervals. And that is actually, we have seen this similar behavior. By the way, this estimator, this is going to be consistent for alpha naught. But it will not be root n consistent. And then if you care about building confidence regions, that will be a problem. So let me just give you some intuition how it behaves if you try to do that. So I'm going to use logistic regression as an example, just to have some procedure here. And so here is the data generating process. I have binary outcomes. So this expectation gives me probability of the outcome being equals to 1 given the controls and the treatment. I have the logit function, 200 observations, 250 controls. So the way I'm going to construct the treatment is just a linear combination of the controls plus some random shock, which is normal. And then I generate y's according to this probability. And what are these numbers? Here, cy and cd, they essentially control the strength of this part in this equation. So if this number is 0, it means that the treatment is only this independent shock. If cy is 0, it means that the outcome only depends on the treatment. So by changing these cy's and cd, I can control the r squared essentially in each equation. And that's what I'm plotting here. So here I'm looking at a two-dimensional set of data generating process, parameterized by cy and cd, because I want to illustrate uniform properties. If I want to illustrate uniform properties, I cannot look at one data generating process. I need to look at a family of those. And this is a two-dimensional family. And here is the ideal picture for a rejection probability of 5%. So you should think, if I do each point here corresponds to a configuration of some cy and some cd, that would define a data generating process. I could build confidence intervals, applying this method here, and I could see the coverage. Right? Ideally, if I'm building a 95% confidence interval, that rejection probability should be 5% everywhere for all possible data generating processes. That's what a 95% confidence interval does. So that's the ideal picture, is this flat surface for all data generating process I'm considering. So here would be where D is highly determined by X. Here's where X does not really matter for D. When I do this procedure, that's the picture that I get in terms of rejection probability if I build a 95% confidence interval through this method. So basically, if you look here, you see this thin line actually works. The rejection probability here is 5%, because this line corresponds to the case that CD is 0, which means the treatment is independent of the controls. So model selection does not matter. But as soon as I start putting a little bit of dependence between X and D, rejection probability really increases substantially. And it's not hard to get 35% rejection probability while I should be seeing 5%. So that illustrates the lack of uniformity of this procedure. And this has been essentially, this just confirms the negative results from Lieb and Potcher for this case as well. So the intuition why is this a problem is the following. Let's see. So basically, when I look at my estimated equation, but now I want to look at it as a function of alpha and beta. Let me look at it as a function of beta, evaluated at beta equals beta hat, because that's what we're using here. We're using this plug-in estimator. So take this function, but we're evaluating at this other point. This is equal by some Taylor expansion x alpha naught beta naught plus the gradient of this function alpha naught beta naught times beta hat minus beta naught plus something that of the order of beta hat minus beta naught squared. Right? Assuming enough smoothness, I have an expectation, so I'm not really concerned with that. Now, this, it's 0 by assumption, by identification assumption. This has a square here. We know we have a good rate. These will be negligible. So these I'm not really concerned with. The problem is this bias. So what happens that this bias, this guy is going to be square root s log p over n, this bias, which tells me that I have a misspecified model when I try to do this second step. And the misspecification is of this order, which is much bigger than 1 over root n. So that misspecification will create enough bias to destroy confidence regions. It will not destroy consistency. This is going to 0. So I will still be able to get alpha hat going to alpha naught, but not with the precision I want to build nice confidence regions. Essentially, it goes back to the idea that in high-dimensional estimation, beta hat is a non-regular estimator for beta naught, so it does not converge at root n rate. So this term is bigger than that, and this term will actually dictate the behavior, the asymptotic behavior. And we have seen that lower bounds for Lasso are actually of the same order of magnitude as upper bounds, so it's really problematic. Now, the way we're going to try to get around this, and I'm constrained to be here, I guess, is to come up with low bias equations, which essentially boils down to use some instruments. Now, so instruments might sound a little bit strange if you never saw them. So I have my identification equation, but I'm going to have a valid instrument if I have this extra variable, which depends on d and x, potentially, but it's such that it still preserves the identification, but gives me two other things also. When I take derivative with respect to alpha of this function, so this is a function of alpha. I add a true value, but then I evaluate at alpha equals alpha naught. That's different than 0. So basically, if I change a little bit alpha, I can see in this equation that creating a difference. So I can still identify it. But when I take derivative with respect to beta, Now it's a function only of beta, and I evaluate at the true value, that derivative is 0. So what happens now? So this is this magical random variable. So what happens now is that when I use a plug-in estimator and I try to redo this calculation, so we go expected value of m w alpha naught beta. Now I'm going to do for my new condition, evaluated at my plug-in estimator. It's equal to w alpha naught at beta naught, z naught, plus the gradient plus something of the order of beta at minus beta naught square. Okay, same expansion. The only difference now, so this is still 0, but this derivative is also 0 by definition of the instrument. So this term also 0, and then I have a second order term which is going to vanish. So what this instrument allows us to do is to kill the first order bias, and we are left only with the second order bias. And as long as we can estimate beta hat at an n1/4 rate, or faster than n to the 1/4, the whole bias is actually smaller order than root n, and so it will not affect my first order asymptotics. That's essentially the idea. So once we have this, then my misspecification is too small to cause any damage in my confidence region, which is of the order 1 over root n. And then I can actually proceed into the calculations. So Danzig's selector, Lasso, post-Lasso, they give you the square root of s log p over n. We're asking for that condition. So essentially we need, it suffices to have s squared log square p to be little o of n. And then we get the guarantees we like. And these essentially match what we did last class. This is the type of conditions I had to actually use in the proof there. So, and this is, to some extent, the idea of this low bias equation has been around for a while. This is not a new idea. What is new is to actually use it in these high-dimensional settings. Right? So the idea actually goes back to Newman and to achieve some additional robustness to perturbation. So he used that in the 50s. But indeed, this idea was used in 2010 in this IV estimation. There, it was the instrumental variables were given to us because that's the IV setting. And we finally saw that we can potentially use the same ideas towards these other models. And this type of kind of more robust estimators, which use this orthogonality to avoid the non-regular aspects of beta hat, has been used in kind of in the low-dimensional case by many other authors. So if I have this instrument now, a very natural estimator would be just check hat that minimizes 1 over n summation of my moment conditions alpha beta hat. So now I can use the plug-in estimator here if I have that being used with the instruments. And that's how. Now, the natural question at this point is how to get an instrument, which would be this magic variable that it still allows you to identify things, but has these two derivatives condition being satisfied. So let's go back to some examples. So in the case of least squares, we have our equation, we have our moment condition, and we have the instrument there. So what we want to do is to take a derivative with respect to beta of this function. Well, this does not depend on beta, going to drop. This does not depend on beta, it's going to drop. This one depends on beta, so I got x, z0. So I need my instrument to satisfy this orthogonality condition. But I also need to be, when I take the derivative with respect to alpha, to be different than 0. So I want a variable that is correlated with the treatment, but uncorrelated with the controls. That's what we're chasing here. Well, turns out that this is precisely what the residuals of this regression is. If you regress D, the treatment, on the controls, the residuals, they're going to be orthogonal to the controls. So the expected value of xi, vi, is just given x. And this is 0 by construction of the regression. So it satisfies the first condition. But then when you take the expectation of D and vi, we get expectation of x gamma naught plus vi times vi. That's expectation of vi square plus expectation of vi xi gamma naught. But by the first condition, this is 0. But this is definitely different than 0. So basically, to get the instrument, I just set z 0 to be equals to the residual of this regression. And this is what essentially the hidden equation that we discussed last class. Now, when we go, let's say, for quantile regression, our moment equation is a little bit different. Our moment equation was indicator of y less equal than d alpha plus x beta minus tau. So we have expected value of indicator of y less equal than d alpha plus x beta minus tau. This multiplied by z. Now I can actually take expectations with respect to y. So I get expectation with respect to y basically tells you actually that you only get probability, like that's the cumulative distribution of y evaluated at alpha d alpha plus x beta minus tau z. Now we need to take derivatives with respect to each one. The derivative with respect to alpha give us derivative of f. It just gives you little f, the density function, evaluated at d alpha plus x beta times d times z. And the derivative with respect to beta will be just expectation of derivative, and it can be this, d alpha 0 plus x beta 0 times xz equals to 0. This is different than 0. So that's what these conditions are doing here. So I need my instrument to be orthogonal to the regressors weighted by the density of y, but correlated with the treatment weighted by the density. Well, again, an equation shows up. If I just take the least square, look at the least square model for the weighted treatment on the weighted controls, the residue of that satisfies this condition, which will ensure that the first one is going to be 0, and the second one is going to be different than 0, precisely by the same reason. So the residue of this equation would be my instrument. When I go for the logistic case, similar things will happen. The derivative of the logit function will show up, and I get another equation. Turns out that this is a valid instrument, but actually the optimal instrument is actually to use square root of the weights instead of the weights. So in this case, it actually leads to a better estimator in the end. So that would be the instrument. So what's the estimator at the end of the day? At the end of the day, would be just use some Lasso with the corresponding criterion function to give you these preliminary estimators, alpha hat, beta hat. Construct your instrument, typically via weighted Lasso regression. And then you apply this, minimize this condition, this criterion function, which is weighted by the estimated instrument. In the case of logistic regression, that's what it boils down to. First step, you run Lasso logistic regression on the first equation. That's the standard procedure. The second step, you run a Lasso, regular Lasso, but your y there is the weighted treatment, and the variables are the weighted controls, and you keep the residual. And then you just run this, you minimize this expression, essentially. This is a moment condition, and this is your instrument. Turns out that each step actually uses a different method. These weights will need to be estimated, but they can be easily estimated with the solution of the step 1. Essentially, once you have consistent estimates for alpha naught and beta naught, that's what you need for the weight. You just need consistent weight. You don't need super precise weights. And this is what the uniform properties of this estimator looks like. So it's not completely flat, but it's for a huge degenerating part, a huge set of degenerating process, it gets you very, very close to the 5% rate that you expect. Now, you see here that he is up to 10% on this very extreme case. This corresponds to the case that you have a little bit of dependence of y and x, and you cannot tell d from x too much, right? They actually confounded too much. So that creates stronger requirements. That's why it picks up a little bit in that particular point. But definitely an improvement with respect to the first procedure. And then there will be conditions, and this is an analysis that works very, very generally. So the conditions for different methods, for different problems will be different depending on the specifics. So I'm trying to think what to do. Yeah, so I have some additional results that I could discuss, or try to give a very brief sketch of the proof. But essentially, the proof boils down to controlling approximation terms and exploiting the orthogonality condition. you apply it, so in the end of the day, the main result is precisely asymptotic normality that holds uniformly for data generating process that satisfies this condition. So in smooth cases, that would be logistic regression, the least squares. Essentially, you need the sparsity square log cube p to be little o of n. But in non-smooth cases, which are known to be harder, for instance, quantile regression, we have that indicator function. So this here, we have a discontinuity that creates issues for asymptotics. That translates into stronger conditions. We need S cube to be able to treat in that case. And we need some kind of smoothness conditions on these functions. But since we have the expectation, that typically it's not a problem. But over that class of data generating process, we can achieve uniform consistency, uniform validity. And those estimators are shown to be same parametric efficient, at least when you compare it to the asymptotic variance in the case of the finite pKs, the fixed pKs, we get the same expressions for the asymptotic variance of them. And you can build these confidence intervals for alpha hat as usual under that condition. Now, there are a couple of additional results that I would like to say. So first one is that if you want to build different confidence regions, it's definitely possible. In particular, if you look at this of the criterion function, which is self-normalized, this turns out to have to be asymptotically pivotal. In the case of quantile, is actually pivotal. So we can show that at the true value, this criterion function, properly scaled, goes to a chi-square in terms of distribution. So we can actually invert this region. We can pick all the coefficients alpha such that this rescaled of the criterion function is below the particular quantile of the chi-square. That defines a region. Doesn't need to be an interval. It could be kind of a separate region, a non-convex set. But we can show that it will have the right coverage uniformly across the data generating process. And that's typically the picture that goes with it. That's the chi-square, red line. And this is the approximation that we get in finite sample through multicolor. And this is the coverage performance of this other confidence region that we get. So everything I said up to this point was for one coefficient. But typically, people want to do this for many coefficients. So consider the following setting. So in the case of logistic regression, suppose that inside the logit function, we have many coefficients of interest, P1 coefficients of interest. So it's just many of them. The way you do, you're going to apply this method for each one of them. For each L coefficient, you're going to take all the other coefficients to be part of X, and you apply this procedure for each one of them. So you can define these quantities based on the moment conditions. But the bottom line is that you can actually get this confidence, this representation for your error that will allow you to do inference. In particular, you can do confidence intervals simultaneous for all of them. So each one of them goes to a normal 0, 1 when properly rescaled simultaneously. This is pointwise, but we could also do, based on some recent results from Victor, Dennis, and Kango, basically, we can actually try to do some joint estimation. So we can construct this Gaussian process here where with this covariance matrix. And if we look at rectangles, we cannot, so that's the one thing. We cannot look at any possible region. In this high dimensional space, it's too much flexibility. But rectangles, they are essentially variations of L infinity norm. So in terms of entropy, it's a super well-behaved family of set. And as long as log P1 to the 7th is little order of n, we can actually show that, the chance your estimators are in a particular region is converged to the chance that this process is in that region. In particular, we can do simultaneous multiple testing, and we'll have the right coverage, where the critical values can be computed by simulation of this process. And that allows essentially us to implement these through a multiply bootstrap method. So basically, these can be consistently estimated based on the data, and then we can just show that the bootstrap multiplier will be essentially will have the same distribution as the Gaussian process over the rectangles, and then we can proceed to implement these where the critical values now come from the bootstrap, and that becomes actually doable in finite sample. And then we have some additional results for more general models. In particular, we allow for endogeneity of the model. So basically, the estimated equations are biased. As long as you have additional instruments, you can do it. But we also extended the analysis for functional data. So my y now is indexed by some u, and u lives in some set. So what that boils down, that we need, for every u, we're gonna get an alpha u and a beta u. So that requires us to extend even the Lasso results to functional data. So actually, we are running a continuum of Lasso estimates to get these coefficients, and then will allow us to estimate a bunch of quantities of interest. But in the end of the day, to do this inference properly, to do simultaneous inference over these functions, we can actually rely on bootstrap techniques. So that was the nice connection from the previous one. And then I have a couple of just a few examples to show how this, in some specific empirical applications, to show how it actually works. The first one is more actually a methodological point, that trying to understand risk factors in India. So basically, not in India, in the effects of malnutrition and other risk factors on. So what we have here, we have a bunch of controls, and we have a binary variable saying that codes if a child has malnutrition. Then, in this case, we have only 30 variables and 40,000 observations. So what we want to use this example for is to make the point that if you try to do model selection, even in this context, that's a very good context that you can imagine. You have a lot of observations. You might run into trouble if you do the old way. But the full model becomes a benchmark. Because actually, I can actually run the model with all the variables and get estimates there. Basically, this is more than enough observations. So I can use this benchmark to see how what we propose behave to respect to the benchmark, and how the traditional approach behaves with respect to the benchmark. And here are just a few results. So basically, this is the full model. This is the traditional approach. And this is what we are proposing. Essentially, with respect to the true model, the full model, we are always within half a standard deviation from each other. And the naive approach, actually, out of the 30 coefficients, there were 11 which were substantially different. These are at least 3 standard errors away from from what you should get using all the variables. And that's kind of what we see that actually got some wrong. And we can actually see some of them actually fairly different signs. Yeah, this is particularly bad. But just to make a point that even when you have a lot of observations, model selection will be an issue fundamentally if you're building confidence intervals. So another example that we did this, we look at this example from Freakonomics that tries to see what's the causal impact of abortion on crime. So this is based on a paper of Levitt and Donahoe for 2001. And basically, you are chasing the alpha naught, which is the impact of abortion rates 17 years ago on current crime rates. Right? And they discuss a lengthy discussion about the causal mechanism that would justify such approach. So basically, the analysis at the end of the day suggested that there was, after control for confounding effects, there was actually a negative impact. And after it translates everything, would be that if you change abortion rate by 1 standard deviation across states, murder would decrease by 9%. So that was kind of the conclusion. And they were 95% confidence that would be between 5 and 13%. That's kind of the conclusions. So we decided to take their data, just enrich it with more flexible variables based on their controls. And here's what we found. So the first line is just to make sure we replicate what they did. So that essentially matches what they did. If you throw everything in, we have 300 variables, 500 observations. You only get noise at that point. But if you do just Lasso, essentially you recover their results. So, which tells me that the way they were selecting models is very much with a prediction problem in mind. So there's just selecting variables which these stats are big, keep those, bad p-values are going to throw away. When you do the post-double selection, which is one way to see this type of estimators, the result goes away. Essentially, you are within 1 standard error of 0, so your confidence interval contains 0, so you cannot reject the null hypothesis. There is no effect. Another application was this on conditional convergence. There was this theory of absolute convergence for poor countries would eventually catch up richer countries because they will grow faster. After a country, it's easier to grow when you are not fully developed. So in the long run, poor countries could catch up. And then they decide, OK, this could be true potentially if there is, if you control for proper things. Because if there are a lot of corruptions, wars, it's going to be very hard for any of such country to catch up. And so that's, if you get data on GDP, so basically the richness of a country is measured by log of GDP per capita, and growth rate is what you're trying to predict. And you want the effect of the richness of the country. So if you have a negative effect here, that would support the idea that these countries would catch up. Like more developed countries would grow slower potentially. And so this is what Barrow and Lee did. So in their model, they got an effect of essentially 2%, and which was statistically significant. If you use all controls, you get something similar. Single selection preserves the result. Double selection also preserves, actually makes it even a little bit stronger. So that's kind of consistent in that. So here's just to make it a point that these more robust methods, they select more variables, but it's not clear that you're always going to be closer to 0, or that you're always going to have bigger standard error. these things can go both ways, especially in heteroskedastic models. And I think I'm about time. So the other examples would be instrumental variables examples, but I think I will let you guys go now. And so just to conclude, is that I think we reach a point that we have a fairly good understanding of estimating coefficients for predictions, and we start to scratch the surface for estimating confidence regions. But now, by knowing a lot of prediction, we can easily combine estimators to come up with estimator for more interesting cases. And this is one example that you can actually achieve some good properties, very desirable properties to do inference, which, at least in econometrics, might be the most interesting question. So thank you for listening.